months before launch, and now we're 400 and some odd days after launch. So far more exciting to be showing you early results. I know many of you contributed to the mission. Before I leave this slide, I'm representing 500 to 700 different people who worked on all of this, including, as mentioned, Chuck McLean. I wouldn't be here without him because A, he hired me, B, PACE doesn't really happen without the groundbreaking work that he did ahead of time. So I do have a little bit of a history of the mission, and when I can't answer questions, I brought up the backup. But yeah, this is Building 7 SCA. You walk in, glass doors on the left. This is our girl. She might not look like much to anybody who doesn't love Star Trek and remembers the Borg. And she's pretty. We'll walk through the 3 different instruments and all of this. But, usually I put this in just to remind everybody that I'm a lowly oceanographer who doesn't really know how to manage anything, but yet here I am in this position. So I will regale you with tales of oceanography and why you should care about the ocean. I will dabble in atmospheric science. Not quite as good there. It's a fluid you can't see. Water. So anyway, with that, this is kind of going to be the flow. Some of this, if you were here in September of 23, you'll have seen before. But I want to just present the context of why a mission like this is so important. And then we'll kind of walk through the history, and then I'll show you some early data and other ways to be involved if it interests you. So, starting at the top, literally, of the atmosphere, the beauty of missions like PACE and Lotus and VEERS and CWIFs, and I was hired to work on CWIFs way back when, is that these are these beautiful passive radiometers that make the invisible visible. And it's really fun to come to an event like this and go to a bar and say, I can prove to you that I see microscopic algae from 400 miles above the sea surface. It's really fun. So in this case, we're looking for a microscopic universe in the atmosphere that comes in the form of atmospheric aerosols. We'll talk about those. And then my bread and butter, which is a microscopic marine algae called phytoplankton. Basically form the base of the food chain. So walking through them real quick. So early on, we're selling a mission of discovery. There's a lot of things that as I will show you, we didn't anticipate to be revealed with PACE. And that's really, really hard to sell in the sense of why are you going to invest all this money on this when we have a Lotus and we have a VEERS, what's new about it? So the way I would always answer this is, I have a quiz. Do you like breathing? Do you like eating? If the answer to either of those is yes, then you really care about what phytoplankton are in the water. And we're blind to that without the technological advance of PACE. Well, why should you care about phytoplankton? They come all different shapes and sizes. They have different nutritional values. They sink at different rates. They play many, many, many different roles in the marine ecosystem, and they operate just like land plants. They're just forests in the ocean, just like there are forests on land. How do we see them from space? Well, they are small, but they are mighty. So just one of these little coccolithophore cells is like 10 microns, super teeny tiny. But the densities are like thousands of cells per millimeter. So the way I try to describe this is if I pulled one hair out held up, you can't see it. But if you're looking at my head, you can see that there it is hair. It's there. Why you want to have a mission that lasts a really long time is you can do time series analyses on these. When I started the mission, I had more hair. It was also brown. So basically the same thing your eyes are doing here. If you can see a lot of something in the color of it, it really gives you a lot of information about what you're looking at. Don't be fooled. There are phytoplankton that are actively trying to kill you. This is Western Lake Erie. This is a cyanobacterial bloom, so it's it's bacteria.
The same one
it contains a neurotoxin called microcystin. And this is the water intake for the city of Toledo. So there's a lot of really, really good reasons to know where the good algae are because they feed fisheries, they keep beaches open, restaurants, economies sustained along the coastline. But there are also those that close drinking water intakes, contaminate bodies of water where cats might swim, golf courses, and things like that. So moving to the atmosphere, basically we're trying to discover the same thing, but this, instead of looking at microscopic algae, we're looking for atmospheric aerosols. And an aerosol in the atmosphere is anything that's not a gas, so including clouds, but we kind of treat them differently. But it can be dust, it can be haze, wildfire, volcanic eruptions, sea salt, any of that. And they all come in different shapes and sizes as well too. And with an instrument like MODIS, you can see that there are aerosols there, but you can't see the species of aerosols. So that's kind of where our mission comes in. Because they're important in how they impact other planet. They form clouds, they get formed by clouds. They see phytoplankton blooms. Phytoplankton can actually see cloud formation. A lot of these aerosols will either absorb or scatter radiation. So some of them will go in the atmosphere, some of them will go in the atmosphere. So knowing what's there is really, really important, not just the radiation. Okay, so how does this all work for both oceans, atmospheres, and even land? The principles are pretty much the same. I'm going to keep this ocean focused. But the color of anything you're looking at is really just dictated by how photons interact with that system. So in the case of PACE and MODIS and VIRS, we're passive instruments. We're not shining any lasers, radar, anything like that. We just observe the color of sunlight. And so these happy little photons make it from the sun to the sea surface, through the atmosphere, they're scattered. And if they're lucky enough to penetrate the sea surface, then they interact with what's in water. And no matter what photon you are, you have two fates. You get absorbed by something, absorbed into something else, or you get scattered into another direction. And in the case of everything, but in particular the water, different colors of photons scatter and absorb differently. So all red light in any body of water eventually goes black, very, very sharp. It's a really cool camouflage mechanism for some fish, like squirrelfish, that if they're near the surface, they look red. If they're hiding in a cave, they'll suddenly look gray if there's red lights down there. So in this case, the phytoplankton in the water and other suspended sediments and so forth dictate the interaction of different colors of the rainbow. Water, some of these photons are lucky enough, again, to get back out of the atmosphere and find their way to the top of the atmosphere. And then the reality is all the instruments we're talking about here operate really just kind of like your eyes. They interpret, they measure color, and they allow you to interpret what you're looking at. So like in its simplest form, think of when you're looking at the water, you're thinking it's pretty clear. That's just what your brain is like. If you're looking at green water, something's going on in there. Brown probably has suspended sediments, or tea, the dissolved organic matter running off. What the instruments are doing is basically just collecting these photons, but instead of looking at the whole spectrum all at once, they're doing it one by one to the top. And MODIS and VIRS era, we're really only looking at somewhere between 6 and 12 different colors. We'll come back to that. So the core satellite measurements for everything we're going to be talking about is basically just light intensity. Light intensity of different colors of the rainbow. And from that, you can do some very simple and some very, very elegant things. This is the basis of our climate data record for the past 40 years in the field of ocean color. It takes a ratio of blue light to green light and relates it to a photosynthetic pigment that's ubiquitous in all plants, land or ocean, called chlorophyll A. And you can see if you squint, even though it's in log space, there's a relationship you can have for this forward thing. So this is a funny way of saying if I can see blue light and green light from space, I can tell you the concentration of the photosynthetic pigment, which means I can tell you is there a lot of phytoplankton or is there a little phytoplankton. And you can basically, if you do this for every pixel you measure, you can start making these really cool maps. So in this case, I'm looking at the concentration of this microscopic pigment in the Chesapeake Bay from orbit. The reds here mean there are a lot, the blues and the purples mean there are a little. So now, if you build a 20-year time series, you have compressed your senses all the way into space, and you can watch our planet breathe. So this is a combination of CWIS and MODIS and VIRS. It is 20 years, 2.5 minutes. If you just stood still and watch it, you can actually see the breathing of your own planet here. The colors on the land are intuitive. Greens are forests, white is ice, and browns are deserts. In this case, the deserts of the ocean are represented by these purples that we have in the South Pacific. And the forests are all of these greens and reds that keep appearing and disappearing. If you look at this long enough, you can see the patterns actually start to change. You can see that the ocean deserts are starting to expand as the sea surface warms. The intensity of the reds and the greens get higher and higher. But I haven't told you anything about what phytoplankton community is actually there. I'm just telling you that there is is an algae of some sort. That said, to me, this is more important than what I mean, this is NASA's greatest Earth science achievement. Is 40 years of being able to watch Earth. All right, so before PACE launches, this is pretty much where we are. So what you're looking at here is a model that shows distributions of 4 different phytoplankton communities, just in time and space. And down here, you're looking at a model of different aerosols being moved around the globe here too. The important word here is these are both models. So while this is real data measured from space, this is a model, and this is where we're going with PACE. This is why we launched this and spent $940 million was to start making direct observations. And so what we pretty much promised the community and the world is the following series of data products, and it's a long list. But what I hope you take away from it is it's a very complete list of the entire Earth system. So again, we're just photon collectors, so on top of the atmosphere, we're just looking at radiance, which means that signal has a contribution from the atmosphere and from the ocean or from land. So starting at the top, the kind of things we're looking for are anything related to aerosol speciation, plus the physical properties. How vertically high are these different aerosol plumes? We can't really see that until emission release happens. What is their optical density? How thick are these plumes? What are their speciations? Do they ground carbon? And so forth. Cloud optical properties as well too. And in this case, it's all the same kind of things, heights, thicknesses, but also the thermodynamic phase. We're looking at liquid clouds, we're looking at ice clouds. This new information from space on global scales. Drilling down, of course, we're looking at how land and water reflect light. We can do some really interesting things with oil slicks, actually, with weather instruments as well too, which was kind of one of the oddball discoveries we're starting to realize. And then you get to where I'm most comfortable, which is looking at the water column itself. So in this case, light penetration. Is there light penetrating that goes deep enough you can have seagrass formation, or is it a certain bay where you don't really see the bottom? How light is absorbed, how light is scattered, is it available for photosynthesis, what pigments can we reveal, can we see anything related to phytoplankton health, species. I say phytoplankton a lot, but we're looking at other dissolved in particulate matter as well too. So carbon, things like that. And then if the water is shallow and clear enough that you can see all the way to the bottom and back, then there's an opportunity here also to do water classification, looking at coral, looking at sea grasses. And really kind of want to know that too, because again, that's an ecosystem that supports shellfish and a lot of other industries. And I will show you some early data on land, which is amazing. They've always kind of been off to the side. You notice they don't appear in our acronym, but this mission has been revealed to be a really, really great pathfinder for doing new vegetation as well too, which is super exciting. So we could be place, just put an L in there for land. All right, so that's why we're here. In introducing Chuck, I think someone mentioned 2001, which means this mission is old enough to legally drink. So I take no credit for this. This is Chuck and a colleague of ours, Mike Werdell, but this is the family tree. And it really kind of begins back in an era where we didn't have the consumers market we have today. Right now, PACE is flying with a bunch of other amazing instruments from NASA and our
You left out CCCS, the maximum 70 years.
You know what? I was.
Yeah, older than you.
I was 4. But there was a 60th anniversary for NIMBUS a couple of years ago, and Chuck and my boss G couldn't make it, so they asked me to talk about ocean color. And so I found the textbook for grad school that had the CCCS image and said, "Oh, this is what got us interested in all of this." But yes, but sadly, CCCS wasn't with us in 2001. But anyway, I just want to point out that as NASA colleagues, you know how long it takes to get a mission from an idea into reality. And this was a formula study which I spent a ton of time on that. If memory serves, was interrupted because of that 9/11 event.
What happened?
So I brought you here.
Mary Cleve asked Goddard to lead a NASA-wide carbon program formulation. All centers invited. And so myself and Forrest Hall, if you remember him, he was on the terrestrial side. We led that study. It took us 1 year, 3 workshops, and a number of mission design lab studies over in Building 23. We delivered the report, went up to the NASA administrator. He liked it. He merged it with a supercomputer initiative. Took it to OMB, and they said, that's great, we like it. But what happened yesterday killed it, and that was 9/11.
But you persevered, you had,
Yeah, we didn't give up.
you know, all of these other exploratory studies. You'll see the name of the place has really kind of evolved over the years. It took a little bit more firm foundational step forward with the 2007 decadal survey, because there was a mission there called ACE. And that was going to be a 4-instrument observatory, an ocean radiometer, polarimeter, a LiDAR, and a cloud radar. So 2 active and 2 passive. And they even had science teams right here, and Climate Initiative plan, Mike Freilich and others put out. The decision was made to split that into 2 pieces. And so you had the passive part, which was ocean radiometer and polarimeter, and then you had the LiDAR and the cloud radar, less mature form. And that's where the acronym was born. We were not always Plankton aerosols, we were pre-ACE. So formed a science definition team. Not long after that, it was Chuck and Carlos and others led. Fast forward to December of 2014, Payson gave me a real mission. This is a letter of direction to Goddard from headquarters saying, go create this. Happened. I got hired. Jim was there as well too, February 2015. So I've been with the mission, not the longest, but close.
Who's the signature?
The bottom is microscopic. So if you fast forward 9 years, here's what we experienced. No particular order. We did have a 34-day government shutdown in 2019. We were canceled in the White House 4 times. You can use your imagination. And that, we had a number of amazing community science teams formed. One of the earliest missions ever at NASA to build an applications and an early adopter program into the ecosystem of phase B and C instead of much, much later. So they got in time where they could be influential, but they couldn't drive instrument requirements because that ship had sailed. Agency senior leadership's changed a ton. We got all of these odd little technical requirement creep things like delay tolerant DTN networks. Other things that just kind of percolated into program management nightmares. A broken prism. So one of our 3 instruments, a contribution from the University of Maryland, Baltimore County. This is cute little polarimeter. It was doing its vibration test. It was 9 seconds left in the last direction. The prism bombed and broke loose, and it just let loose glass. So you will see that stuff. They persevered. That was in February of 2023, and they delivered the instrument in October of 2023. It was really fun. And then there was 4.5 months of nothing of the work and a phased re-entry in the whole pandemic and all that stuff. So it was a long, I know everybody's got their stories, this just feels like a long one. But that said, 1 o'clock in the morning on February 8th, we launched. I put the launch video in, but I usually start crying. I don't want to do that. So, but today is day 425, so we're creeping up on 500 days, and I think we're order of 6,500 orbits right now.
So this was a polar launch from the Cape,
Yes. Yeah.
which is something fascinating
Right.
in and of itself.
Yep.
I didn't know you could do that.
It was the first non-military one in 40 years.
Yeah, just Said he watched it from the tape. I said, you need Vansburg. I said, no.
Right, yeah. I was lucky enough to have that odd experience of sitting in the Kennedy, basically the big table where all these important people like say go, pieces go, pieces go. 3 days before lunch, they hadn't finished the agreement with Cuba yet, which none of us knew. So we're really close. We're going to be okay over Cuba, which I understand is the reason we stopped doing lunches. Anyway, so I've showed you a picture, but I haven't really described anything about the instrument system yet. So we are 3 instruments in the total package here. Primary instrument is OCI, Ocean Color Instrument. It's not a really great name because it does way more than ocean color. It's aerosols and land as well. But the Orca experience is the reason Goddard was able to take on this, and it led to this instrument here. I will show you details in a second. The other 2 are contributing instruments. They're both multi-angle polarimeters. First is HARP-2, which is the one from University of Maryland that I had mentioned before, and then the other is a contribution from a collection of entities in the Netherlands as well too. And we'll get into the details of how they play off of each other, but it was really great for us because in that letter of direction, it said go forth and find us polarimetry, but it wasn't a requirement. But it was kind of a nudge, go find us polarimetry. So we did a bunch of RFIs and studies, realized we couldn't afford it, and then these 2 great organizations raised their hand and said, I think we can help you out. All right, so the major advances of the mission are probably 7 or 8 really great things. I'm just going to focus in on 2. The first for OCI and the other for polarimetry. So, the most substantial contribution of OCI is that we have moved from multispectral radiometry, just several colors of the rainbow, into full spectrum spectroscopy here. And this is important to get down into that speciation I was talking about before. These are brilliant missions. These are very, very intelligently placed wavelengths in the visible and shortwave spectrum. They do a fabulous job for separating a signal from phytoplankton from everything else in the water. So they're doing exactly what they're meant to do. And again, it's not telling you what species are located in there. So it's only really when you can measure all of the different colors that you get to that. There are other missions that do this in Europe, but they do not do it every day. They have coverage that is usually 14-day repeatability, and if you've ever been on the water and you go back looking for days, it never looks the same. You're looking for something that's growing, that doubles and triples on the scale of hours to days, in a 3-dimensional fluid on a rotating ellipsoid. If it's not there today, it ain't there tomorrow. So I did some PhD work on the Arabian Sea, and it's going through a very, very profound shift in community there, particularly right around now, actually. The northeast monsoon is finishing up. And the base of the food chain there historically is this diatom-based system, which is what most fisheries really, really thrive on. So you have a traditional fishery system. But given changing oxygen levels and other things, this bully called Noctiluca, which is a heterotrophic dinoflagellate, which means heterotrophic means it eats things, and then it also photosynthesizes. And dinoflagellate means it can move its head on the tail. So it has gone in, wiped out everything else, does this every year. The origin and the mechanisms for it are only starting to be understood. So you need the vantage point of space. And one of my favorite things, especially in classrooms, is why do you need to do this from space? It's not just because the ocean is 71% of the Earth's surface and you can't be everywhere at all times. Satellites are time machines. I have a new idea. I've got a 20-year data record. I just go back and reprocess the whole mission. So in a place like the Arabian Sea, which is very, very difficult to study, let alone get on the water, having the vantage point of space really clues you in on all this stuff. So if in the videos, what you're looking at here on the x-axis is just color from red to, from purple to red. Y-axis is just kind of a metric of what the satellite would see. The diatoms, the good guys, are in black. The Noctiluca, the turtle food bad guys, are in red. And with VIIRS, you can see there's only one piece of unique information, so you really can't tell these 2 things apart. But with a hyperspectral study from an instrument like OCI, there are so many differences in the spectrum that now you can start saying, I see this versus I see this, or I see mixtures of them. this every 1 or 2 days, depending on cloudiness, is a massive step forward scientifically. OCI. Okay, so Ocean Color Instrument basically drove all of our requirements. It is a complicated machine. The atmospheric and the communities basically got everything they needed for free, because if you can do it for the very, very dark ocean, and you can build a nice dynamic range so you don't saturate, then you can do it for those other things. So it stands on the shoulders of SEWIS dominantly, but also some of the severe parts. It's a scanning radiometer that goes from ultraviolet continuously into the near infrared. We're even shining a light on detector space down into ultraviolet. So it's 2 spectrographs overlapping around 600 nanometers in red. Resolution is always 5 nanometers, but it's 2.5 nanometer steps. One of the really cool things about the instrument is you can configure that to be smaller or bigger steps as well, too. The way the physical is. You do shortwave infrared. It's a single science pixel typically striping, 1 kilometer footprint. You'll have a copy of this. I don't have to read it to you, but it is it's big object that does things very, very well, which I will show you. And unlike anything before. There's the picture. It's big riding lawnmower sized object. All right, so the other innovation here is multi-angle polarimetry. So the bonus of mirrors and CMOSs and CZCSs of the world really only view a single piece of real estate at one viewing angle. Multi-angle information is new in terms of information content. So if you're just looking straight down at this piece of land, it would look like this. If you're looking 70 degrees forward, the same piece of real estate looks like this. So these differences are really useful pieces of information in terms of teasing apart what you're looking at. And then the polarization is really important too. This is the parking lot bangs, normal intensity there, degree of linear polarization on the bottom, which is basically just the ratio of horizontal and vertical polarization to the total intensity. It looks completely different. So when you put all of this together, you're really taking a massive quantum leap forward in information space in terms of what you're looking at. And a lot of these little things don't seem like much, but that's the missing information to get to layer heights of aerosols and clouds, thermodynamic function, and all the microphysical properties we can't see with our eyes. Also, since I mentioned camouflage before, polarization is a really, really good camouflage mechanism for marine species too. And in fact, others view the world with only polarized light, and apparently that is a very good predator to shrink too. So it's all around us. All right, 2 polarimeters. They complement each other really
By the way,
nicely.
excuse me.
Oh yeah.
That was built at Goddard, OCI?
OCI was built at Goddard. Yep.
Where's
Built in
that?
5. I had its own little lab run in 5. And the spacecraft was built as Goddard as well too. And integration was all done at Goddard too. Yeah. I mean, of course, there was a lot of like the shortwave infrared detector system was built by SDL at Plankton, but Goddard really all had the charge here. The 2 polarimeters just play off of each other. We won't belabor it up too much, but you'll notice one is 4 wavelengths. One is continuous from the near ultraviolet to the near infrared. HARP 2 is a very, very wide swath and views the world from 10 to 60 degree, 60 different viewing angles, whereas SPEX 1 is narrow swath and only has 5 viewing angles. So you've got one multispectral, hyperangular, you've got the other is hyperspectral and multiangular. They really, really play off of each other nicely. So instead of one big supersonic instrument, you have got a pair. Yep, just up the road. So the nice thing about having the capabilities of HARP 2 is that it does a really nice job with its multi-angular capability to get to cloud optical properties. It goes far beyond what we can do with OCI alone. And because it's a really, really wide swath, it plays really well with the sky also. And with SPEX 1, it can be characterization of aerosol microphysical properties that we can't do with OCI alone. So I hope what I'm instilling here is that the 3 instruments playing off of each other is a quantum leap. And just as a little bit of an aside here, my expectation is data science and basically computing within science realms will advance rapidly because this is so much information that nobody like myself does not use it. We really, really need to start having these brilliant children and scientists. So the punchline here is with the niches that we fill, this move from multi to hyperspectral radiometry, absolutely essential. You cannot move forward in the aquatic universe without it. There is no other plan to have, there's no current plans to have its predecessor, its successor, either in the US or in the maybe coming out of the Copernicus program that's in Europe. But otherwise, it is one of a kind in its global coverage. Let's see. The fact that we're measuring UV and have two 2-micron bands is really great for a bunch of atmospheric and cloud studies. The multi-angular dimensions of polarimetry is, I don't know, it's a lot of information. It's all new. It's really, really rad. And one thing we didn't talk about is that this is the first ocean color instrument that's actually tilted, like CWIS and CCCS in a long while. So the running joke in our lab has always been, oh, this is great, yours is great, there are ocean color capable and ocean color instruments. Because when you don't tilt, you're not an ocean color instrument because nobody wants to look at this thing. This was one of the hardest things I had to advocate for because it is a 300-kilogram beast with a rotating telescope, perpendicular plane of flight, and I wanted it to tilt 40 degrees and settle in less than a minute. They figured it out, and it was really awesome. Where are we today? We are 1 year in, so we are still in our 3-year prime mission ops. Presumably, we'll go into mission extension. There have been a number of anomalies, as we all have. In any mission experience since launch, the flight operations team is really remarkable. They've been working so hard on these things, they can't do everything else they want to be doing. There's been some process of resell, basically growing pains on how you fly. Since I knew this was a very Goddard friendly, built a lot of stuff around, I figured you'd enjoy it. No matter how much I'm telling you it's awesome, there are still nuances, but and it doesn't help that we're in a solar X. The South Atlantic anomaly has been kicking that poor little polarimeter called specs butt since launch, but we know how to reset real quick now. And like I said, the flight operations team, this is from another talk, just let you enjoy the fact that it's a really great group of Goddard. The flight software sustaining engineering, flight software, thought, mission models, they're all very, very proud. So, okay, we took the bold move of launching, and then 63 days later, put in our first data products on the street, uncalibrated, minus pre-launch calibrations, and just said, this trio of instruments is performing so well that right out of the box, the community should start using it, which wasn't easy in the sense of saying, it's not perfect, we're in the process twice this year. It's something that our group has actually become very proud of, and it is a testament, particularly for this how kick-ass that instrument is. We're finding things that are so down in the weeds because it's performing so well. And we've already done 2 processing so far. This is a testament to the community too. They're starting to use it. The calibration data is coming in. They have ideas for algorithms, so we're constantly being challenged to reprocess the entire data set to get new products out on the street. So that's been a lot of fun. It was a long year, but it has been really great to be able to do this because we're solving a difficult problem that's now fundamental core that we don't have. All right, so wrapping up, let me show you just some imagery from the instrumentation. I will say, I think everything I show you is not just brand new for us, but brand new for the air science community. So this is a map of little aerosols from HARP 2. As you said, it's a really, really nice swath, which you can actually see how wide it is in some stripes in the imagery there too. But even not being perfectly calibrated yet, they are able to start teasing out different species of aerosols, which is profound. So you see the separation of dust coming from Sub-Saharan Africa, which is going to be deposited here. Blue, there's forest fires. resolution and so forth. This is first 6 months of specs one aerosol data. It's an aerosol, so you can see a little animation from cloud fracture. It takes a little while to fill in the entire globe, about a month to see every piece of real estate on Earth. And, signal scattering albedo is pretty new. What we're really, really kind of excited about is that they are starting to get into some atmospheric properties that we just don't have for direct observation yet. So the combination of these two polarimeters is really, really good. Now, the problem with plastic in the ocean is that it gets photo bleached so quickly that it tends to lose its color. And even though if you were to take a net and get to a lot of it, it is very dispersed in the water. Maybe with polarimetry and maybe with some of the shortwave infrared stuff. We actually have a science team member working, which is and easily the question I get asked the most. So it's a good one. This is the first land, not in our acronym. This was the first discovery we shared with headquarters. Let me see if I can restart it. This comes out of Fred Kummer and one of our younger person's group. So what you're looking at are 3 different photosynthetic pigments from land plants. Now, all of these algorithms are basically multispectral. They don't use a couple of wavelengths. They have been tested really well using radiometers out in towers in the field. The reason that this is groundbreaking is that there has not been an instrument that has flown that has had all the wavelengths on it that can do all of these algorithms simultaneously. So this is the first view from space on a daily scale of what these products are, going from regional tower measurements all the way to the top of the atmosphere.
Shown this to Jim Tucker.
Yes, you bet. Yeah, for sure. Yeah, no. So this is the realization of one of those things that is so important to like center directors, like we don't know what we're going to learn, and this pops out of the box first, and it doesn't even great, so at the atmospheric chemistry lab, Joanne Joyner and Zach Fashionat, they didn't think OCI would have the quality to do an NO2 retrieval in the atmosphere. And again, out of the box, they found out that it's, now I know we can do this with Tempo and Tromomi, but what I want you to see is how small the OCI footprint is relative to the other instruments. And if you're looking up here, you can actually see NO2 plumes going down highways. Actually, surprise. Yeah, so again, the algorithm is, there's a lot of machine learning in all of this, but it's another cool way of looking at Earth. Now, switching to the ocean. So this is the first phytoplankton community product that came out of OCI. This was only even released as a test product a couple of weeks ago. And it's from a postdoc that actually worked at Goddard. So what you're looking at here is just a false color image. That's what the ocean would look like if you were floating top of the atmosphere. What you're looking at here are 3 different colors representing 3 different phytoplankton communities, little guys in the open ocean. My favorite thing about this is this feature here is not visible to the eye, but yet with an algorithm like this, you can actually pop out and see something. So that was fun, and it only works in the Atlantic. Now you're looking at the same thing, North and South Atlantic, but now on monthly kind of rolling time scales too. So, I mean, we haven't even got around to publishing this yet. It's really hot off the press. But as you might imagine, headquarters is looking for all kinds of good information, so we're feeding them as fast as we can. But this was the promise of PACE originally, so I mean, this is Chuck and others had in mind the ability to do something like that from space. And because I don't want to fool you, say all phytoplankton are good. This is a view of a harmful algal bloom, a red tide, off the coast of California in September. So we had a big field campaign out there, aircraft. We had ER2, we had Twin Otter, we had a couple of different boats all collecting validation information. From the Twin Otter, you can see the red off the coast there. That's the red tide. And then this is a view of what that looks like from OCI. The reason you can do it with OCI and nothing else is the algorithm to get to this needs ultrameta, and there's nothing else flying with ultrameta. So when we keep thinking of hyperspectral being like we need every part of the spectrum, that's true if you're using a derivative algorithm or spectral matching, but it's also true just because everything responds somewhat differently in that spectrum. And if you can just pull those little pieces out, it's pretty cool. That was in January. That doesn't, but I actually have a backup slide on the fires too. This was before and after the two hurricanes, Milton and Helene, went through the west coast of Florida here. And you can see the response in the before and after. It takes a little bit of, like when you see images after a hurricane, you would see a lot of structure here that wasn't there the day before. But most of that is just resuspended sediment. So everybody wants to say there's a biological response there. It's not. It takes a couple of weeks for that to form. But you can see within a month, the bloom that was already starting to form there had accelerated, and that is because of the passage of the hurricanes through it. And again, this is from a spectral region of OCI that's not a Okay, so I'm running out of time. Just say everything else. If I have just intrigued you enough, you want to learn more about the good, the bad, and the ugly of the instrumentations, we've got a great website. We even have a page that says, here's all the parts that don't work, just to be completely open with the community. This is just showing that, I don't know if any of you ever did anything with the AeroNet network at Goddard, but that has provided a major data source for us. So much so that within, I think, 160 days of launch, 160 days from first light, I was able to go to headquarters and say, because of this network and because of this instrument, we've already met our mission success criteria for all the uncertainties on our core radiometric products. So, and that's the real reason that I put this one in here, is just be like, holy crap. Well within a year, we've met mission success criteria for the quality of the instrument. We've got a great community out there. We have a third science and application team. This is headquarters funded. They're sitting on top of the mountain coming up with new ideas. We've got a dedicated validation science team. No hypotheses, just go out, collect data for us. This is the experiment in California I was talking about. It was a logistical ballet of 2 aircraft and 4 ships. And God, I just can't believe they pulled it off. 30 days out there, achieving all of their goals. We've got vector calibration teams out in the field and an applications program that is very active. So simply just sharing, it's not just Goddard patting itself on the back. There's a lot of energy in the community. And so even the youngest members of our staff, when they were able to travel, would go to meetings and get high fives like they were rock stars. So, and then we're trying to get stuff out there too. We've got a community newsletter. We've got this is where I go when I try to figure out how to code. But what I'm really, really excited about too is I've been able to pick up twice now independent funding the host data hack weeks, where we're able to pay for like 40 or 50 different participants to come to University of Maryland, and then we can just embed them with cloud computing and teach them how to use the data and so forth. So, and our next one will be in August. I've got 40 slots. I think we have 109 applicants from all over the world. So there's a lot of good energy.
So how we used to learn how to use data sharing.
Yeah. Correct.
Maybe Nerd Week.
Yeah.
Space Data Nerd Week.
They are so much more advanced than me in these things that when we did the first one, my postdoc gave the intro talk on how to access data from the cloud, and then for the next 4.5 days, I lost all hearing and just practiced that while they went on and did other things. So wrapping this up, I think the punchline here, and this is actually from a program manager downtown Woody Turner, but I think it resonates, is that the step from Lotus to PACE is just like going from Hubble to Plankton. It's that much more. Yeah, cool. I think I'll stop there since it's almost 10 after.
Don't forget that there's an exhibit at the Visitor Center for you to see.
And a little immersive experience at the Kennedy Center for another week as well, too. That's part of that. Yeah, would you like me? I brought a copy of the thumb drive. I was asked, I think, if you wanted to take a copy, right? Yeah. You know, I can send you a link.
Okay, that'd be good.
Yeah.
Yeah, we have great, no one has customers.
No, I think there's one person who's now the chancellor, I think at Rhode Island.
Oh,
Plankton.
yeah.
I think she helped make it happen from the National Academy of Science Cable Survey and headquarters viewpoint. Jack Day told me once that, Paula wanted this mission, and I said, Jack told her, don't talk to me, go to the academy. They're doing this, the cable survey, sell them. They're the ones.
Yep,
So we got to give our hats off to Paula as well.
Chuck and I have known her for forever.
She was program manager for ocean biology for what, 13 years?
Yeah.
Which is very long
Yeah.
for program managers.
Her perseverance, really drove this to the I answered all your question. Oh, not Jim's.
No, I'm wondering how the data system evolved. Right? Are you doing processing on commercial web services, or are you doing it in-house still?
A little mixture of both.
Yeah.
Right now, this is again one of the requirements creep we experienced. All data distribution is migrating to cloud, Amazon Web Services. They weren't mature enough to do data processing in the cloud for us yet, so we're doing on-premises processing and pushing it to every station. In fact, I think the browser that we've had for 40 years, just a couple of weeks ago, was retired.
Okay.
I was just wondering if you could explain again, you were saying how important it was that you probably meant that instead of just later looking,
Oh, yeah,
looking ahead, I just don't
So
know that I really understood that.
So I'm going to borrow something from Gary Davis then. He did pace yoga, so this will be in the right plane. But so we're polar orbiting the South Pole, ascending. So we're coming up over the South Pole, and the instrument is looking behind us, so it's not looking into specular reflection of sunlight coming off the sea surface. And then when you get to the subsolar point, it'll tilt forward so that the sun's behind it again. The reason for this is since we're looking for color, I mean, just like looking out of an airplane where you're looking into the sun, you can't see any color anymore. It is just bright light in your face. So that becomes data we end up masking. To make the requirement to do this tilt, we actually did a study and revealed that relative to a nadir pointing instrument, and it depends on time of year, if we can do this 40-degree tilt, and we can do it in roughly a minute, we're recovering 17 million square kilometers of ocean that we would otherwise lose every 2 days. So for context, that's like the size of South America. So it's a huge amount of real estate that would otherwise is useless information for us.
Did it also get you more coverage?
It does. So by doing this, then you can never get rid of the entire. You know what? I could show you. So this is for different instrument, but anything that has color here is really lost to sunlight. If you tilt, it collapses to this size. So that's it. So this is real data from Lotus without tilt. Let's see this with. So you can see the tilt pattern in here. This is where it's tilted. But the same day, you're getting much, much, much more coverage. And then because of that, if you take the per orbit delta and what you lose here relative to here, the recovery is that big number of 15, 17 and a half. So, but that was a huge engineering lift. CWIS was teeny tiny, so it wasn't that big of a deal. This was a fight with 400 a few times. Oh, and just since it was mentioned, it's not just to have something there. This was in response to, we were trying to be very delicate about this. This is the January wildfires. It's an instrument like HARP-2 can actually separate the smoke from the fires from dust that's just happening naturally. OCI, again, getting back to land, is burn severity indexes to that you can see the scorched area. Now, you can do all of this with Landsat. Difference being that Landsat's repeatability under 4 weeks, whereas OCI seeing it they play off of each other, they don't replace each other. Sorry, I'm starting to lose. Yeah, this was a tough one to get out because we knew we could do something with it, but it's pretty devastating. Yeah. Thanks again.